Yeah, I say it's an important one. I think the OST, they've had several release questions on this concept. And Pythagorean theorem will still come up. They'll ask questions on that. And definitely some trigonometry stuff. It's amazing. Okay, let's do... I got to do two proofs to start, and then we're just going to talk a little bit about extending the Pythagorean theorem. So that's it today. Similarity and what happens with similar triangles when they're right triangles. So what I want to do, and this is a standard they say I need to teach you, show using the Pythagorean show using similar triangles how to get the Pythagorean theorem. Derive is how to come up with the formula. So what we're going to do, and this is again a released question. They had essentially this diagram, and they showed how to prove the Pythagorean theorem. We're going to show I have a right triangle. There's angle C is, well, BCA is marked there as a right angle. It's a right triangle. And an altitude. If you remember, an altitude means it makes a right angle. It's not marked on here, but it actually both sides, right? That's what an altitude is. I'm first going to show those three triangles are similar. Then we're going to prove, once the triangles are similar, the Pythagorean theorem. Okay, let's see. So similarity in right triangles. So let's prove the triangles are similar. And what I've done here, giving you the statements. We'll discuss them, but then we're just going to fill in the reasons. All right, so first we start with, well, I guess I should put it more. The right triangle, the right angle, and an altitude. That's given. Angle CDA, I already marked it, and BDC, again, I already marked it up here, are right angles. I kind of already mentioned it's because of an altitude. I'm really combining 2 and 1. It's because an altitude means perpendicular. Definition of altitude. But then definition of perpendicular means forms right angles. So I'm kind of combining 2 and 1 there. Altitude means right angles and altitude means perpendicular and perpendicular right angles. So these are right angles, and CBA is a right angle, BDC is a right angle, and it was given up here BCA is a right angle. And if they're right angles, they're congruent. All right angles are congruent. All right angles congruent. So what I've done, we did this on the review from Unit 4. Small, medium, and big triangle. We're showing they're similar. Right? So that's what these three triangles are, small, medium, and big. And we have one angle now in all three triangles congruent, the right angle. We need one more angle in each triangle. And again, it's the same as what I did on that review. In the medium, I'm going to go medium to big triangle. Angle A is shaded. Right? Medium triangle, it's angle A. The big triangle also has angle A. They're congruent. It's the same angle. Same thing with angle B. That's in the small triangle and the big triangle. Small triangle, angle B. Big triangle, also angle B. Those are the same angles, so we say reflexive. So now, here, and I should say, so these medium and big, this was for those two, and angle B was the small triangle and the big triangle. And now, between these two, the medium and the big, two angles congruent, right angles and A. Small to big triangle, the right angles and angle B, two angles are congruent. Therefore, I've named them DBC is the small, SM. CBA is the big triangle. They have two angles congruent, so they're similar. And so, of course, that is angle-angle similarity. And the same thing for the medium and the big triangle. DCA is medium and CBA is still the big triangle. So I've showed the small triangle and big triangle are similar, and the medium and the big triangle are similar by angle angle. If the big is similar to the small and the big is similar to the medium, then the small triangle and the medium triangle are also similar. This is transitive property, connecting those. Normally I just put transitive property. I'm going to just clarify. Normally it's just between segments or angles. So I'm going to put transitive property of similar triangles. I went ahead and grouped that the third one, we already knew it was similar to each of these. And so all three are similar. So angle, angle, and then transitive property.
So
yeah.
For the reason for step 2, if you just put depth and altitude like on a test, would that be considered wrong?
I think it'd be fine. Yeah. I can just, honestly, a more thorough proof would be 7 steps. It'd first be altitude, perpendicular, then perpendicular right angles, then right angles congruent. I just grouped those two. It's a good question. I think it with altitude. So we showed the 3 triangles, small, medium, big, are similar. Good on that one? Angle, angle, angle. Again. And now what I'm going to do is, since the triangles are similar, so I'm going right off from the last one, last proof. The triangles are similar. We just showed that. That's given in this one. How can we show the Pythagorean theorem? And it's just doing proportions. So I've labeled this. We'll see later in the year when I give you the example that the state gave. They didn't label it H and Y. They just left it as like, it's called BD. You call this CD. I called them H, Y, X, just to make it over here a little bit easier. So the triangles are similar, and so I'm going to do proportions. So here's the first one, the ratio A over Y. A over Y. Now what this is it's actually a big triangle to small, and it's doing the base of each one. So in the big triangle, here's the top, here's the base. In the small triangle, here's the base as well. Okay, so did that ratio, because all the ratios are equal because the triangles are similar. And then C to A. In the big triangle, C is the hypotenuse, and in the small triangle, A is also the hypotenuse. And so they matched up. This was like the base side, the first one, and then C array was the hypotenuse. They did that proportion, which is true. And then we just switched and did another proportion that's true. B to X. Now that's the long leg in each triangle. It's like the heights. So in the big triangle, long leg. In the medium triangle, the long leg. And then C to B and the big triangle is again the hypotenuse. So the big triangle, this is the hypotenuse. In the medium triangle, B is the hypotenuse. Okay, so that was proportion. Just got to match it up. The sides have the same ratio. I'm going to write corresponding sides of similar triangles are proportional. Yes, you could also write definition of similar triangles. And guys, from there, that's all we need, and you solve that equation to get the Pythagorean theorem. Solve that equation. And by the way, so we're getting, in the big triangle, a squared plus b squared equals c squared. So let's see, what do they do next? What you probably would naturally do with this, cross multiply. Right? A times a squared. C times y, cy. Right? Same thing over here. B squared and c times x. Multiplication, if you want to say cross multiplication, that's fine as well. You could say cross products, you could say cross multiply, or you could simply multiplication twice, actually. So I don't care, cross multiply or just multiply. Okay, what we're going to do now is I'm going to take this left equation. what I'm going to do is add something to both sides of the equation. I'm going to add, on the left side, I'm adding b squared. On the right side, I'm adding cx. Now, you'd say, aren't I adding different things? Isn't that illegal? Well, no, b squared and cx are actually equal. Right? So it's like if I'm solving an equation, right, and I add 3 to both sides, right, for the addition. I'm adding the same thing to both sides. Here I'm adding b squared, and here I'm adding cx. They are equal though. So I can do that. They look different, but it's actually just like adding 3 to both sides, since b squared equals cx. Sometimes, here, if you don't like that, you can think of it as I'm just adding the left sides to get a squared and b squared. And I'm just adding the right sides to get cy plus cx. All right, so either way, I'm adding. It's just addition property. So I add the left side, I add the right side. I'm adding the same thing to both sides. So it's really just addition property. The left side is exactly what we want, right? A squared plus b squared. The right side, we need to get to c squared. Well, right here, I can factor out a GCF of c. All right, I'll be left with y plus x. This is a good one. Well, there is no GCF property. Who remembers what property? It's one of these. What property this is? Distributive, yes, because if you were going backwards, it'd be distributive. And that's all we got, both directions. So GCF is really distributive property. Thank you. So then here's the cool part. Y and x are right there. Well, y plus x is actually c. Y plus x is that whole segment, which is c. So we replace y plus x with c. Substitution. That's just what we knew it was. And finally, c times c is c squared. And again, that's simplifying. So it's substitution. A nice little proof for the Pythagorean theorem. It wasn't until this past year that there released a question. It was kind of like this. It was filling like 2 or 3 lines of the proof statement and reason. So I figured I'd show you all of it. So this one, get a proportion and you solve it. Anything else I can clarify on those proofs? Those are good, very fun. Okay, so flip the page. I want to say a few things about Pythagorean theorem. Now, I know you know what it is. We've used it a lot this year. I want to do an extending example, and then tell you what Pythagorean triples are. That's pretty much wrapping it up. As a review, the legs are the non-hypotenuse sides. So hypotenuse across from the right angle. The legs, you can call A or B, it doesn't matter which one there. So I wanted to clarify the Pythagorean theorem versus its converse, because I don't think we've talked about the converse. Right? Converse is reverse theorem. So the Pythagorean theorem, yeah, I know you know what it is, but it says this. If a triangle is a right triangle, then the sides, A and B are the legs, and C is the hypotenuse. A squared plus B squared equals C squared. The converse, though, if the sides of the triangle equal A squared plus B squared equals C squared, then the triangle is a right triangle. So the converse shows that you, here, I think I said it here. The converse shows that you have a right triangle. Yeah. The converse just shows that triangles are right. I'll just put shows triangles are right. That was just something I wanted to talk about, just to clarify. I think it was because I saw, like, as a reason, converse of Pythagorean theorem used as a reason. So just wanted to clarify that one. Okay, I want to do one example, tell you about Pythagorean triples, and that's pretty much it. So let's do, I called it an advancing Pythagorean theorem example. It's not just, here's 4 and 7 and 5, 4 squared plus 7. It's more than that. It's a word problem. All right, so let's think about it. I'll draw a picture for this one as well. So an artist wants to build a right triangular frame. So here, I'm just going to, it's a frame, it's a right triangle, in which one of the legs exceeds the other by 1 unit, and then the hypotenuse exceeds that longer leg by 1. We'll use algebra to show the sides, and that there's only actually one triangle that works. So the shortest side we don't know to start, and then we know the longer one in the hypotenuse. Let's call it x, because I don't know what it is. So if that's x, where's that? One of the legs, the longer legs, exceeds that one in length by 1. So the longer leg is greater by 1. So I should call it x plus 1. Yet again, the hypotenuse goes up by 1 as well. The hypotenuse exceeds the longer leg in length by 1. So it's x plus 1 plus 1, which is x plus 2. And now we know it's a right triangle, and now we can find that we can write an equation, Pythagorean theorem, and solve for x and get the side lengths. And so that's what I'm going to do. I'm going to start with the short side x squared plus by b, x plus 1 squared. Make sure it's in parentheses, not just 1 squared. Equals the hypotenuse, x plus 2 squared. Alright, so let's work it out. The x squared just comes down. Do not say this is x squared plus 1. Right? I really need to. I'm going to take an intermediate step. This means times itself. And so does x plus 2. So I'm going to FOIL. I got to FOIL these to work them out. X times x is x squared. 1 times x is x. 1 times x is x. And 1 times 1 is 1. Then, this is time equals. Over here, similar thing. X times x is x squared. Again, let's do FOIL first. Outside is 2x. Inside is 2x. And the last is 4. Okay, I'm just going to combine like terms, and then I will finish solving. So on the left side, I got 2x squared. 1 here and 1 there. I've got 2 x's, and then a plus 1. On the right side, it's just combining the middle terms to be 4x. The 2x and the 2x. Once we get here, it looks like nothing else will combine or cancel. So we're going to get everything on one side and factor. So I'm going to subtract x squared from both sides. And so 2x squared minus 1x squared is 1x squared. By the way, I mean everything on the left, so that's a positive 1x squared. If you got everything on the right side, it would be a negative 1x squared. So now I'm going to subtract 4x. So 2x minus 4x is negative 2x. Subtracting 4. 1 minus 4, negative 3. Alright, and 0 is left on the right side. And now I can factor. And it will work. So two numbers that multiply get negative 3. It's got to be 3 and 1 combination. That's it. Let's see. Negative 3, right? So that they add to get negative 2, it would be negative 3 and positive 1. And so we get 3 and negative 1 as our answers. However, the negative 1, like right there, can't have x because it's negative 1 side length. And so it's 3. So that's the only one. If there would have been, if this second one would have worked, there would have been more than one right triangle that would have worked. This says show that there's only one right triangle that works in this equation. So here's what it is. 3 has x, 3 plus 1 is 4, and 3 plus 2 is 5. Those are the sidelines. Perimeter 12, 3, 4, 5. So again, we set it up, Pythagorean theorem. I had to FOIL each of these, subtract and kind of cancel some things, and then we got 3 and -1 when we factoring. Anything I can answer on that one? Okay, last thing I want to talk about is Pythagorean triple. Has anybody heard of a Pythagorean triple? No, you guys didn't do that. Okay. What? Yeah? Maybe? Okay, I didn't know, because you've done Pythagorean theorem before. Your teacher might have just said, hey, that's a Pythagorean triple. Pythagorean triple, it can just help you solve a question. It can help you recognize things quicker. It'll save you a lot of time. That's what it's beneficial for. Maybe a couple years ago, maybe it was on a test, like state test. It will not be, in my opinion, I don't think they'll directly ask you about a Pythagorean triple. But it's going to be very useful to be much quicker to solve. For example, if you saw this triangle, I immediately know what this side is because of Pythagorean triples. I don't have to do the work. If you didn't, you'd have to do a squared plus 15 squared equals 17 squared and work it out. So it saves you a lot of time. All right, so Pythagorean triple is simply 3 numbers that work in the Pythagorean theorem. They have to be whole numbers, though. So if they're not whole numbers, they can still be numbers that work and be a right triangle. But Pythagorean triple is 3 whole numbers. For example, the most common one, and one I want you to recognize and remember, is 3, 4, 5. That's a Pythagorean triple. 3, 4, 5. All whole numbers, that's the smallest Pythagorean triple there is. Also, just so you know, there's an infinite number of these. They just keep getting larger, but that's the smallest set of numbers, 3, 4, and 5. Let's see, so quick reminder here. I talked about this briefly last year. Yeah, triangles unit, 2 units ago. That in order for it to just work, the 3 sides have to be this. The sum of the 2 sides, of any 2 sides, must be greater than the third. So for example, I'm already jumping the gun on here in this one. These 2 sides are 3, and that's not bigger than 4. So this isn't actually a triangle. However, if any, usually pick the smallest 2. If any of those 2 sides are bigger than the third side, it's a triangle. It's a right triangle if it works in the Pythagorean theorem. So for example, these work in the Pythagorean theorem. They're not whole numbers though. So that's a right triangle, but it's not a Pythagorean triple because they're decimals. As soon as you get something like above the 3, 4, 5 though, it's a Pythagorean triple because they work in the Pythagorean theorem and they're whole numbers. And it's a triangle. So here, if I was doing is 3, 4, 5 a Pythagorean triple, you could check by putting 3, 4, and 5 in the Pythagorean theorem. And if you get the same thing on both sides, it's a Pythagorean triple. So let's see, what do I want to do here real quick? I want to tell you some of the most common ones. Let's check 2 and 3 real quick. Let's do these. So I already checked it is a triangle because 5 and 12 are bigger. The sum is bigger than 13. Let's check now if it's a right triangle. I'm going to do 5 squared plus 12 squared. Yes, I listed them out of order. 13, the biggest one is always C. Remember that? Biggest value. If it's going to work, has to be the hypotenuse. Why did I write C? I'm sorry. 13. Sorry about that. So we try them out and see if they work. 5 squared is 25, 12 squared is 144, and 13 squared is 169. Really, you can put equals. It's really this question mark equal to is actually the symbol. Because you're checking to see, you don't know if it's equal yet. But when you add these, it is 169. So it's a right triangle, these sides, 5, 12, and 13. And since they're all whole numbers, you would say yes, it's a Pythagorean triple. Let's finish up with 3, and then I'll tell you the most common ones. So right away, this is not going to be a Pythagorean triple because square root, not whole numbers. But it still could be a right triangle. It can still work. So let's try it out. Square root of 2 squared. It is in order, by the way. 4 is the next one. And then 3 radical 2 is the largest number. And you notice I put parentheses around these? The square root ones, because over here on this one, sometimes students will do something like this, and then they'll only square the radical. But it's really the whole thing squared. So 4 squared is 16, and radical 2 squared is 2. Right, they cancel each other out. Alright, and then on the right side, let's see, you square each of these. 3 squared is 9. That was a 2. Radical 2 squared is 2. And these are each 18. So it's a right triangle. It is not a Pythagorean triple because the numbers are not whole numbers. But it's at least a right triangle. To finish up, I want to tell you the 3 most common, they're the smallest ones as well. 3 most common Pythagorean triples. I already told you the first, 3, 4, 5. The next one is 5, 12, 13. We saw that in 2. And the next one was that example I gave how I knew the 15 and the 17 one. The next one is 8, 15, and 17. Notice that the biggest sides always have to be. So this is the one I said, hey, I automatically know this side down here. That's it. Without doing any work. That's why these are helpful. Okay, now, I want to say this about Pythagorean triples. You can form any other combination by multiplying all of these numbers by a whole number. So, if I multiply all of these by 2, I would get 6, 8, and 10. That is another Pythagorean triple. So that's why another one is 6, 8, 10. You could easily recognize that. Or if I multiply by 3, I get 9, 12, 15. Multiply any of these up here by 1, 2, 3, 4, and just go on forever. That's one reason why there's an infinite number of these. So even something like this. If I gave you this is 500 and this is 300 and you knew it was a right triangle, what would you say this side is? 400, nice. Right? Because it's multiplied, it's this one multiplied by 100. That's all I got. Anything else you guys see up there? Questions about Pythagorean triple?